For my next introduction, we can have the speaker up already on the screen. I do not need my screen, but it is my distinct pleasure to introduce Lucas from Volatile AI. He's again one of those people who's coming here for the second time, and I'm very, very pleased. He has a very nice title that intrigued me. He's going to talk to us about smell label predictions with eNose, IMS, and GCMS, LCMS-based models in 2 different industry use cases. I'm very pleased to tell you that Lucas's outfit, his company, is actually out there sniffing things just like aromics. So this is no longer science fiction. There are companies out there really, truly sniffing things without using human noses. So without any more introduction, please welcome Lucas Lopez and from Volatile AI. Thank you. Go ahead. There you go.
Thank you, Andres, and thank you for the introduction and all the team organizing Osmocon's conference. Hopefully you can see my screen.
Yep, you're good.
Great. So yeah, last year I introduced our electronic nose platform, Scout 2, which is the device you can see on the top right. Along last year, this year we have also incorporated in our toolset an eye mobility spectrometry, so an IMS, which we adapted to have the same concept of our Scout, which is basically easiness of use, and no need for a trained technician to use the device, right? So we want to take existing commercial technologies on site in production environments. So normally when we take samples, when we work with customers, we take samples from them and we run them through these devices, but also in parallel, we run them through GCMS devices and tasting panels to obtain labels. And normally what we do is to train models to recognize these labels using the signals from our devices. So today I'm going to present 2 use cases that we did during last year. One of these is the yeast fermentation for the pharma industry. So this was in cooperation with Xiling. It's a startup which is doing fermentation for psilocybin and benzothiazepines for treatment of depression. And basically for them, it's very important to monitor this fermentation cycle because that way they can interact with it. And normally lab solutions would take days, and therefore they're interested in a fast screening solution. Well, we found out to our surprise that the IMS was a great device for this, and IMS is a very fast device, but would give you peaks in the same fashion as the GCMS, just much faster. We could see a direct correlation with the target compound of interest with and one of the peaks. So we were happy to see that. But of course, smell is more than that. Smells implies a mixture of chemicals creating a perception, right? And I guess this second use case is more relatable to that, which was coffee screening. So we have been sampling coffee together with Lavazza for several months. And the point of interest here was quality control. So they wanted to see if the beans of origin that they are using for making their blends were mixtures of different coffee varieties, or if they were wash or natural. And well, we ran all these samples with the GCMS and also in parallel with our IMS and our electronic nose. And well, you can see results here. We achieved a decent F1 score for classification of 80% with IMS and 60% with our electronic nose. And well, maybe if you are familiar with some publications in this space, you are wondering why I'm claiming these are results when you can see in some papers are claiming well, a performance of 90% or higher. And well, on that, I just wanted to point out something that comes up very, very often when we talk to customers, and is that the performance that we can see in the lab almost never translates into the industry. And normally this is attributed to more control conditions in the lab, and yeah, that's part of it. But we think that there is more to it. So there is variance in all the data sets that are there, especially so for chemical data sets, right? And well, one of them is the environmental factors, but also Another 2 points. One is the measurement instrument. So of course, GCMS is very consistent, but when we are talking about devices like electronic noses, metal oxide sensors, they are terribly bad at giving consistent signals. So that's one of them. And then the other one is the variation in the sample themselves. The fact that one variety of coffee shows some chemical composition doesn't mean that the same variety from a different batch is going to show something different. So we realized that, well, we never actually were reaching the amount of data needed. And we made this tweak into statistical bootstrapping that would help us understand what would be the amount of data that we would need to get at least a consistent result and realistic. And well, we saw GCMS, of course, is the one that will require less. It's not used in many production environments for practical reasons. But GCMS is something you can assume being very consistent if well maintained and calibrated. And also the environmental conditions are very controlled, right? So most of the variance you would see in the data set is because of the sample variation. When we go to IMS, at least our IMS, which is still using air as carrier gas, so it's not controlling the environmental conditions that much. We need like 5 to 10 times more that. And when we are talking about the electronic nose, that number spikes up to 50 times. So, well, that's one of the reasons why we think that there is a big difference in between the performance in labs and production environments, mostly because of basically lack of data set for training. Then a different challenge that we have has to do with the exploitation of the available data. And that is the thing is we can gather data with our devices relatively quick. We can have the devices in places and we can collect data, but that data will be unlabeled because it's not really realistic to send the sample to a GCMS lab or run it through a tasting panel, which needs to be done basically at the same moment, otherwise the sample would change. So, well, we have a lot of, we end up with a lot of data from our devices, which is not labeled. And one of the techniques we are trying to exploit here is called self-supervised learning, which basically allows you to train some models without using label data, meaning that they can learn the internal structure of the data. And in a further step, it's possible to retrain these models using your final labels and requiring less data. So we are getting there. It's not that we are getting better performance, but we are getting closer performance between our experiments and the real applications, and more consistent as well. So just very quickly to finish, our future steps are we are currently working in the next generation of our chemical fingerprinting platform that includes well, not only metal oxide or PID, but potentially we could attach other kinds of sensors like spectrometers or the IMS itself. We are also adding some micro GC column in there. And we are planning to use this technology in a EU-funded project, which we have been granted together with a consortium. We'll be working with a number of fantastic universities and other companies in Europe, which is with the goal of detecting and preventing pests in agricultural exploitations. So, and for that, we are also participating in the MIST internship program for MIT students. So we are looking for different profiles of engineering mostly. So if that sounds interesting to somebody, you can find more information on the link below. You can find us under the Lithuanian section. Thank you very much.
That is great. Thank you, Lucas. And what a wonderful treat that you're actually participating in MISTI. We have a MISTI scholar here talking later. I have one question, and then we'll do one question from the audience. And we're about 5 minutes over our schedule, but that's still pretty good for a conference. My question to you, Lucas, is this. You have understood something about the variance of the data and the problems with the noise. Is there something fundamental about GCMS versus the other techniques? Why is it that it appears to have such a difference in how much data you need to make sense of it? Is it in the noise? Is it in the shape? What is it about these data that makes it so different? Why can't it be the same number of data points that you need to train the model, no matter what technique you use?
Yeah, no, that's a good question. So GCMS, well, of course, is consistent, right? The trick with GCMS is that it requires all the calibration, and probably the sampling setup needs to be specific for what you are sampling. So it's not really practical to use it in many production environments. But I would, I mean, as long as peaks can be identified with single chemical compounds, then what you have in there is a very fundamental ground truth, right? Which is the pure chemical composition. Of course, how that is translated to smell perception is a different topic, but at least it's a very universal language. When we are talking about IMS, it really depends. So the first use case that I show had a very clear peak for the compound of interest. So nothing to say there. You don't really even need to train a very complex model to quantify the compound. But if we get into fingerprinting, like in the case of coffee, or yeah, in the case of coffee, for both the IMS and the electronic nodes, we will have a lot of convoluted data and overlapping signals, and that basically means that that you need to look at more complex patterns to actually learn what is going on there, and that basically explains. Yeah.
Great, thank you so much, Lucas. We have a question from the audience. Jessica McGrath was curious if you take into account the receptor expression level.
Sorry, can you repeat?
I absolutely can. Jessica McGrath wanted to know if you take into account the receptor expression level.
The receptor expression level.
I apologize. Ignore this and carry on.
I have a question, Lucas. I evaluated a startup years ago that was doing a fermentation evaluation of wine. So when you said fermentation, it kind of piqued my interest because they were measuring the fermentation bubbles. Mm-hmm. So is there a connection between GSM, the technology you're talking about, and the bubbles of the fermentation process, or is it just different technology?
Well, there is. I mean, I'm not sure what this startup was doing, but I'm pretty sure it was not only about the bubbles, but also the headspace in the fermentation tank, probably. So these bubbles, what they create in fermentation tanks is the pressure that you can actually use to extract your target gas. And but of course, talking about wine, I mean, wine is a very, very complex product in terms of chemical composition. And also has alcohol, which is a problem with I mean, it's challenging working with some sort of sensors, and the CO2 generated. So, well, I mean, it's related, but I think the use case that I presented is simpler.
Yeah. Well, thank you so much for Lucas and Volatile AI. Please keep in the chat with Lucas, ask him more questions, and we can forward them to him. Now, we have a 5-minute break. Please be back by 11:10. Let's say 11:10. We're only 5 minutes late, but let's not keep getting late. This is a bio break only. Go get some water, some coffee, go to the bathroom, but then please come back for our next speakers. Thank you.